What we are going to do for the rest of the lecture is to give several examples of NP-complete problems so that you are familiar with them. Okay? The first example is the shortest simple path. Actually, we shall be giving you the examples in pair. One is P, and a very similar problem, you will see that it is NP-complete. So the shortest simple path is actually P. It belongs to class P. What does shortest simple path means? Say, given a graph G equal to VE, find a shortest path from a source to all the other vertices. Okay? We saw, for example, from Discret's algorithm in data structure that there is a polynomial solution to this problem. And the running time is simply big O of number of vertices times the number of edges. So clearly this is, this problem belongs to class P. But here is a similar problem, but unfortunately there is no polynomial solution to it. Longest simple path. Okay, given a graph G equal to VE, a pair of V and E, find a longest path from a source to all the other vertices. Okay, so the opposite of shortest path, we want the longest path. Unfortunately, nobody has been able to find a polynomial solution to this problem, and therefore this problem is NP-complete. Okay, the proof of all these statements are there in the book if you want to go and study them. But in this lecture, we will not be proving anything, just for you to know example of problems that are NP-complete. So longest simple path is an example of NP-complete problem. Okay, next example, Euler tour. Okay, the Euler tour is belonging to P actually. Okay, what does it mean? Let G be equal to a pair of VE, a set of vertices and a set of edges connecting them. Find a circuit. Notice here we're talking about circuit, not cycle, that traverses each edge of G exactly one time. Okay, now because it is a circuit, if we remember the definition from data structure course, we must visit each edge only one time, but we can visit a vertex more than one. If we have that, it is called a circuit. So that circuit, if it passes through all the edges, then it is called Euler tour. Okay, now there is a polynomial time to the Euler tour, and its running time is simply the number of edges in the graph. So here is an example. Actually, figure A, it has a Euler tour, but figure B has none. Okay, let's go through the Euler tour for A and you will see what I mean. Suppose you start from A, so we visit the edge AD and the edge DC, edge CE, edge EB, come back to C, so BEC. So you see in a circuit, we can repeat visiting a vertex, no issue. A cycle, of course, you cannot. So then we go to the edge CF, then the edge FB, and finally the edge BA. Notice that we have finished, we have visited all the edges, and we have come back to the same vertex where we started. Okay, because of this is called a tour, and it is called a Euler tour. Now, there is an algorithm for finding a Euler tour. And the algorithm can tell you whether there is a tour or there is none. Okay, it's not always guaranteed that there will be a tour. But if there is one, the algorithm can tell us. Okay, and the algorithm can also tell us if there is none. For example, for graph B, there is no Euler tour, as you can see. If you start from A, you can go to D, then DC, then CE, then EA, and then AB, BC, CF, FB. Now we have visited all the vertices, but we have not come back to our starting vertex. To actually come back to the starting vertex, we need another traversal, BA. And that means visiting an edge twice. And this is not allowed in Euler tour. Each edge must be visited only one time. So actually there is no Euler tour for this graph B. Okay, but the bottom line is there is an algorithm that can tell us if there is or there is no Euler tour. That algorithm, its running time is simply the number of edges, big O of the number of edges in the graph. So this is good news. That algorithm for finding the Euler tour belongs to P. But Hamiltonian cycle, which is very similar, unfortunately there is no algorithm for it, and therefore it is NP-complete. Okay, so define G to be equal to the pair VE as a connected directed graph. Find a cycle that visits each vertex of G only once. So we want to visit the vertices this time. We may skip some edges, but we want to visit all these vertices only one time. Okay. Now this problem is NP-complete. Okay. If you are given a solution, you can verify it. For example, for this decahedral, you can see that there is a cycle. Okay, for example, if you start from here and follow the shaded path, you can see that you will be able to visit each vertex without repeating any vertex and without repeating the edges themselves. We have a cycle. No vertex is repeated, no edge is repeated. So this is a cycle. Okay. So this, if we are given this solution, we can easily verify it. Just make sure all vertices are included and that all the edges exist in the graph, and there is no repetition of vertex, no repetition of edge, and the starting vertex is equal to the ending vertex. If you can do that, we have already verified the solution. So verifying is very easy, but so far nobody has come up with a polynomial algorithm for doing that. In fact, the problem is NP-complete. Okay. Another example related to Hamiltonian cycle is a bipartite graph. What does bipartite graph means? It is a graph that you can group its vertices into two. So here we have one group here and another group here, such that all the edges are going from one part to another. So as you can see here, all the edges, they are moving from one side to another side. So if you have that, then your graph is said to be a bipartite graph. So bi coming from the two groups for which you can group the vertices. Now there is a theory that says that a bipartite graph that has odd number of vertices cannot have a Hamiltonian cycle. Okay, and the idea is very easy, because you see, in Hamiltonian cycle, if you start from a vertex, at the end of the cycle you must come back to the same vertex. Now unfortunately, if it is odd, okay, if you leave this part and you go to the other part, you must come back to complete the cycle. But if it is odd, you will never be able to come back. Okay, so therefore there will never be a Hamiltonian cycle for a bitype graph that has odd number of vertices. If it is even, then yes, maybe you can have a Hamiltonian cycle. But if it is not, rather if it is odd, then definitely you will not be able to have a Hamiltonian cycle. So in any case, the main point is that Hamiltonian cycle is NP-complete. Whether the cycle exists or not, so far there is no polynomial algorithm that can tell us. But if a candidate solution is given, as you can see clearly in this graph, we can verify the solution is valid or not in polynomial time. Okay, it can be proved that Hamiltonian cycle is actually an NP-complete problem. Okay, next example is vertex cover. Vertex cover. A vertex cover of G is a set of vertices that every edge in G is incident to at least one of those vertices. Okay, so a vertex cover is a set of vertices, not a set of edges. But all the edges in your graph will be incident to one of those vertices. For example, the vertex cover for this graph is actually consisting of C and B. Okay, why? Because any edge you take in this graph is either incident to B or incident to C, or both, as in this edge. This edge is incident to both. Okay, this is incident to B. This is incident to C. This incident to C, incident to C, incident to B. So all the edges in the graph are either incident to C or incident to B. Therefore, this is called a cover for this graph. Okay, so this is what is meant by a vertex cover. So how do we state this problem? Well, as an optimization problem, it can be stated like this. The vertex cover problem, VC. Okay, given a graph G, find a vertex cover of G of minimum size. Okay, of course, if you add any vertex, this two vertices, it is still a cover. But we want a cover with the minimum number of vertices. Okay, so what we have here actually is the minimum number of vertices that will form a cover for this graph. How do we represent the problem as a decision problem? Okay, so the decision vertex cover problem, DVC, can be stated as follows. Given a graph G and an integer K, determine whether G has a vertex cover with K vertices, at most K vertices. Okay, so again, another bad news is that DVC is an NP-complete problem. Next example, satisfiability problem, SAT. Let us try to define the problem. Given a logical expression, phi, find an assignment of values, false and true, to the variables of our logical expression that causes phi to evaluate to true. okay, to make the logical expression satisfiable. It's better understood through an example. So suppose we have a function f that takes three variables x, y, z, and you can see its logical expression consisting of the three logical operators and, or, and not. Okay, the question is, are there values, zeros or ones, that we can assign to these three variables so that the result of this expression is a 1? Okay, clearly as shown in this table there are. Okay, for example here, if you give 0, 0 and 1 to z, you will end up with a 1. Okay, this is the final result. So if this column gives you 1, it means we are able to satisfy the equation. So, all right, so this is the satisfiability problem. Given a logical expression, can we find a valid assignment of the variables involved that will give us true, or that will satisfy the logical expression? Again, unfortunately, this is an NP-complete problem. In fact, the SAT, satisfiability problem, was the first problem that was shown to be NP-complete. Okay, the proof of this is given in the book if you want to go and see it. This is the first problem that has been proven to be NP-complete. So in fact, it is from this that many other sub-problems can be easily found to be NP-complete. Because remember, as we said, if we can find one NP-complete problem that is easier than a particular problem that is also NP, then that problem is NP-complete. Okay, so it is from this that many other problems were proven to be NP-complete, because this was proven to be NP-complete, and it turns out to be easier than others. So those others also become NP-complete. Okay, the next problem is the CNF satisfiability. This is a special case of SAT, where we have phi is in conjective normal form. That's where the CNF comes from, conjective normal form. So how does that look like? Basically, it consists of AND expressions, which are called clauses, each of which contain only ors of the variables and their complements. This is an example. So you can see this is x1 or x2. This is x1 or not x2. This is not x1 or, so there is no and in these brackets. So these are called clauses. And now you and the clauses. So this is called conjective normal form. Now 3CNF satisfiability is a subcase of CNF problem, which contain only three clauses. This is where the three come from. Okay, so this is an example. Phi is equal to one clause and another clause and another clause. Okay, so 3CNF is a special case of CNF. And another bad news, 3CNF is NP-complete. Okay, so this is an example of how to represent this diagrammatically. So we have the variables, all their complements, we OR them, and now we AND the ORs. So it is in normal form, conjective normal form, and in this case there are three ORs, three clauses. So the 3CNF is NP-complete. Interestingly, however, 2CNF is in P. Okay, there's an algorithm that runs in polynomial time that can tell us whether 2CNF is satisfiable or not. Okay, our last example is a clique. So what is a clique? A clique in an undirected graph is a subset of vertices V prime of the vertices of the graph V that are fully connected. You remember the definition of a full graph from the data structure course. Every vertex in V prime is connected to every other vertex in the V prime directly. Okay, so the question is, does G contain a clique of size K, where G is a graph? This is a clique problem. So if you have a graph like this, does it contain a clique? Does it contain a full graph or a full subgraph of size K? For example, if you ask, is there a clique of size 4 in this graph? The answer obviously is yes, as you can see in this graph. This subgraph containing the vertices that are highlighted in red is clearly a full graph. From this vertex, we can visit this one, and that one. From here, we can visit this one, and that one, and so on for the other vertices. So, in this case, the answer is yes. The question is there an algorithm that can tell you, if you give it a graph and a number K, whether there is a clique of that size in that graph? The answer is no. However, if you are giving a candidate solution, you can verify the answer. So clique is also another example of NP-complete problem. Okay, this is the last example, and it brings us to the end of this lecture. I hope with this you have now understood what is meant by NP-complete. There are many problems that looks very easy, but in fact, so far no polynomial solution has been found to them. All right, we stop here. Thank you very much.